This is going to be the last class of heat transfer. I hope you have learned some basic fundamentals about heat transfer, its applications, the design of heat exchangers, the different modes of heat transfer, both steady state and at unsteady state. And for the last few classes, we were learning radiation and how and where radiation is important, and how can you make furnace calculations which are consisting of more than one surfaces forming an enclosure. So, we saw the fundamental nature of radiation, the emissivity, absorptivity, reflectivity, transmittivity, the relation between emissivity and absorptivity, and what is Kirchhoff's law, when and under what conditions the different forms of Kirchhoff's law are going to be valid. Then we also studied the concept of view factors, and based on view factors, how much of energy coming out of an object at a specific temperature is going to be intercepted by another object which is situated nearby, and the view factor plays a very important role in it. That is, how much of the first surface how much of the second surface is directly visible from the first surface, which is going to be a function of the solid angle and so on. And after that, we introduced the concept of radiosity. So, it's the potential, the radiative potential of a surface which is observed by someone standing just outside of the surface. So, it not only takes into account the emission coming out of the object, it is also going to account for the reflected part of any irradiation on the surface. So, if any irradiation is falling on the surface, part of it is going to get reflected based on the reflectivity of the surface, and therefore, what we see as the true radiative potential of the surface is not just the emissive power, but also the part of the reflection, part of the incident energy which gets reflected. So, it is a sum of the two, and the difference between the emissive power of the surface, had this been a black body, and the radiosity of the surface is expressed in the form of a circuit where Eb lambda t, that is the radiative potential, the emissive power of the surface if it is a black body at a specific temperature, the same temperature as that of the surface, and J being the radiosity of the object. These two potentials are related by a resistance which is known as the surface resistance to radiation, and the difference between the potential of these two, and based on the resistance for radiation of the surface, we can find out what is the heat flowing from the surface to the outside, or how much of heat is to be supplied to the surface to maintain its temperature constant. Based on this, the enclosure method has been developed, and we have seen what it is going to look like for a 2-zone enclosure, what it is going to like for a 3-zone enclosure, how to convert it into star, delta, and so on. So, more or less the concepts which you have already know based on your concepts of electrical technology would be equally applicable here. For example, the sum of all heat coming to a node would be algebraic sum would be equal to 0, and so on. So, when you think of the triangular type of resistance circuit, then you know that one resistance is going to be in parallel with the sum of the two. So, whether it is a resistance in series or resistance in parallel, based on that you would be able to connect the potentials of the two surfaces and find out how much of heat gets transported from one surface to the other by radiation. And as I said before, that the main application of this method is in trying to find out what is going to be the heat to be supplied to a furnace to maintain its hot surface at a constant temperature, or how much heat is going to be received by the surface which you would like to treat if it is inserted if it forms one of the surfaces of the furnace. So, if you put something in the furnace, how much of heat it is going to receive by radiation from the adjoining hot walls. So, those are very important calculations, and with the applications, with the examples that I have solved in the class, I think you are probably you do probably know how it is going to be, how the radiation is going to be treated for an enclosure as well. In all the discussion that we have had so far, we have assumed something very important. For example, the case of an enclosure is usually never under vacuum. Okay. So, the enclosure has some gases present in it. It could be air, it could be nitrogen, inert atmosphere, or something else. In all our assumptions, in all our calculations so far, we assume that the gas or the vapor present inside the enclosure, the gases do not take part into the radiation process. So, as far as the radiative heat transfer is concerned, all these gases are truly transparent. So, they do not absorb anything, they do not emit anything, and so on, which this assumption is mostly true for non-polar gases, for example, nitrogen, oxygen, and so on. But the moment you have polar gases or vapor present in the enclosure, they start to absorb radiation, and they will also, depending on their temperature, can emit radiation as well. Whenever such gases or vapors, these gases and vapors who do participate in the radiative process, it is called radiation under participating media, radiation in the presence of participating media. Now, many of the common gases or vapors that we deal with, which are expected to be present in an enclosure, are apolar in nature, non-polar in nature. So, whatever we have done so far will still be valid. But let us take the case when we have humid air present in the furnace, or the furnace is filled up with carbon dioxide or something else which starts to participate in the radiation process. Then whatever be the emission coming out of a hot surface, and you have another hot surface nearby, and the intervening space is filled with water vapor, then all these emission are not going to come directly to the surface, part of it is going to be absorbed, and obviously as the thickness of this film, thickness of this vapor film increases, more is going to be the absorption. So, if you have absorption on one side of the film, as the radiation proceeds deeper and deeper into the gas film, it is going to be absorbed and its intensity is going to reduce. Now, this reduction of intensity as a function of the thickness of the film, or as a function of the distance travelled by the incident radiation into the participating media, that is going to be important in our calculations. Secondly, the gas itself may start emitting radiation as well. So, there are two aspects to the participating media that we have to be careful about. One is the absorption and second is the emission. So, we are going to start with the absorption of radiation as as a function of distance, that means as a function of thickness of the gas. So, that is the first thing we are going to start with. So, our first thing is the important point here is the participating medium. So, the gas that present in it is going to participate in it. So, examples for this are carbon dioxide, this also H2O vapor, or a combination of these two. So, these are polar molecules. The polar molecules start to participate in it, and they absorb over a wide range. And the complication to this even more is that radiation is concentrated, radiation for these molecules is concentrated at particular wavelengths, these particular wavelengths are called bands. So, that is a further complication which we will also have to keep in mind. But this, coming back to the volumetric absorption of radiation in participating gases, this is a figure which, so this is the starting of the gas film which is participating, is of thickness L, and you have some spectral radiation which is falling on the surface, and it starts to propagate. As it propagates, some amount of radiation is going to get absorbed by it. So, if you have a monochromatic beam of I lambda 0 which is incident on the medium, the intensity gets on reducing. And let us take an infinitesimal thickness of the participating medium denoted by dx, then the amount of absorption or change in the radiative intensity due to the passage of radiation through a thickness dx is given as minus k lambda I lambda x dx. This k lambda is a property which is known as the absorption coefficient, which is going to be different for different gases. So, for a non-participating medium, the value of k lambda would be 0, but for participating medium, for example, CO2 H2O, depending on whatever be the participating medium, the value of the absorption coefficient would be different, and they are known as well. So, if we assume that k lambda is not a function of x, that is, it is independent of x, then this equation can simply be integrated with the boundary condition that at x equal to 0, the value of the monochromatic irradiation is equal to I lambda 0. Then integrating this equation, the intensity, the spectral intensity after a distance L as compared to the spectral intensity at the beginning at x equal to 0 would simply be equal to e to the power minus k lambda times L, where L is the thickness of the film, and this equation is known as Beer's law. So, Beer's law, it states that the intensity of radiation after the incident radiation passes through a distance L is going to decay exponentially, and the constant is known is a property of the gas which is the absorption coefficient. So, what are going to be the use of this equation? The obvious use of this equation is it gives you as some idea of the transmittivity, the spectral transmittivity tau lambda, which would be equal to I lambda L by I lambda 0. Whatever I have written over here is nothing but the definition of transmittivity. So, it would be equal to k lambda L, and the absorptivity which is denoted by alpha lambda spectral 1 is simply 1 minus tau lambda by definition. So, if we assume that the reflectivity to be equal to 0, and this would give you alpha lambda is equal to 1 minus e to the power minus k lambda L. And if Kirchhoff's law is valid, if we assume that Kirchhoff's law is valid, in that case alpha lambda would be equal to epsilon lambda. So, Beer's law provides the spectral emissivity of the medium. So, the important thing that I would like to hear is that it gives the epsilon for the medium. So, what you see over here is that there are Several applications of Beer's law. First of all, it gives you an idea of how much of radiation you are going to get at a distance L if the incident radiation has a value I lambda 0. So, that is what is Beer's law, and this is the traditional definition of transmittivity. So, transmittivity is nothing, transmittivity is simply going to be e to the power minus k lambda L, and since for a non-reflecting surface, which is a valid approximation for a gas, absorptivity and transmittivity are related by this expression. So, what you get is the absorptivity as 1 minus this, and if Kirchhoff's law is valid. So, this is if Kirchhoff's law is valid, then we can write epsilon alpha lambda is equal to epsilon lambda. So, Beer's law gives you the estimate of the value of the emissivity for the medium. So, that is what the now there is few more things we also now. So, we have now an idea of what is going to be the absorptivity in gas mass, but we would also like to have some idea of what is the emissive potential of a participating gas or a vapor, because not only it is going to absorb, since it absorbs it is going to emit as well. So, how do I express the emissive power of a participating medium which is a gas or a vapor? So, our next analysis starts with the gaseous emission, and you understand that for in many cases a hot gas is going to emit radiation which is substantial. Gaseous emission and absorption. So, the aim is to determine the radiant heat flux from a gas to an adjoining surface. So, this is what the aim of the present analysis is, and the method which is used here is known as the Hotle method. This method is a graphical method which involves determining the radiation emission from a hemispherical gas. So, the first thing that is assumed here that it is a hemispherical gas mass with a temperature Tg, and it is emitting to a surface element dA1 which is at the center of the hemisphere. So, the Hotle method gives us first it assumes that there is a hemispherical mass of hot gas, and whatever be the emission it is going to be concentrated at its center. So, if I have a hemispherical mass of hot gas, the Hotle method gives you the emission from the hemispherical mass of gas concentrated on the unit area which is placed at its center. So, that is what Hotle method tells you, and the expression that he has used in order to express this irradiation on the surface is given as this E sub g, that is the irradiation is equal to epsilon sub g sigma T of the gas to the power 4. This epsilon g we already know what this epsilon g is, the gas emissivity, and it's correlated, it's obviously it's going to be a function of temperature, and Tg is and it's going to be a function of temperature, it's going to be a function of the sorry, the it is going to be a function of the temperature of the gas, it is going to be a function of pressure of the gas and so on. So, what he has shown is that the in a graphical way he has calculated what is this value of epsilon g going to be, and this is a function of gas temperature which is T g, and he has got a family of curves, and this is in increasing order of P w times L. So, P w, this is for water. So, for water the value of the emissivity is obtained by a curve like this, where this P w is equal to the partial pressure of the water vapor. How much of water vapor is present in air? Partial pressure of water vapor. So, which is logical, right? Because the more more vapor is present in air, the more it is going to absorb. So, whatever expression that he has provided, whatever values that he has calculated for epsilon g, it is definitely a function of the function of T g, which is the temperature of the gas, but it is also a function of the amount of water present into it at a given point of time. So, the figure that you see over here is for 1 atmosphere. So, similarly pressures, the value of epsilon at other pressures can also be calculated. So, there are two major issues in here. The first one is, this is for 1 atmosphere. So, similar curves must be obtained for higher or lower pressures, and secondly it is assumed that the gas forms a hemispherical enclosure around an object which is placed at the center of the hemisphere. So, these two are limitations of Hotle's approach or Hotle's method. So, for each of the pressure different from 1 atmosphere, you have to have a similar such curve for water vapor. I will come to that hemispherical part later on. Not only that, if you have, instead of water, you have carbon dioxide present in air, then you are going to have a different curve for the value of epsilon g. So, in other words, a pressure correction must be made if the pressure is different from that of the atmospheric pressure. Secondly, if it is something not water vapor, but some other participating medium is present, another family of curves would have to be available in order for us to make the calculation. There is a third part as well. What if two participating medium are simultaneously present in the mixture of gas at temperature T g? For example, you may have air in air both water vapor and carbon dioxide present simultaneously, which can happen. So, if that happens and if that air mass is at a certain temperature, then how do you calculate the value of epsilon g, the emissivity of the gas mass containing different quantities, different partial pressures of water and carbon dioxide present simultaneously. So, you need furthermore charts and so on in order to get an idea of what is the value of epsilon g going to be. So, I will quickly give you an example, and more examples of these are available in your text, which you can refer to whenever you need to calculate the value of epsilon g for a participating medium which is present at a given partial pressure, and when the system pressure is 1 atmosphere or maybe different from 1 atmosphere. So, the first thing is the effect of pressure. Then we are going to look at the effect of the presence of more than one participating medium, and finally, at the last part that we are going to clarify is how to take care of this hemispherical assumption and how to obtain the proper length scale to be used to evaluate what is going to be the value of epsilon g. But first, let us look at the effect of pressure. So, the the for pressures different from 1 atmosphere, this is the figure of a pressure correction which is C W, and you get curves like this. Okay. And these are in increasing order of the partial pressure of water times L, where L is the characteristic length, and this is P W, the partial pressure, plus P, the total pressure, divided by 2. So, this is the partial pressure of water vapor, this is the total pressure divided by 2, and epsilon of water for a pressure which is not equal to 1 atmosphere is equal to C W times epsilon of water when the pressure is equal to 1 atmosphere. So, this is a correction factor which must be taken into account when your pressure is different from that of 1 atmosphere, and you get similar results that are available in literature for other gases. And when you have both let us say both CO2 and H2O vapors are present. If that is the case, then you have in this method you have the correction factor. This is partial pressure of water divided by partial pressure of carbon dioxide plus partial pressure of water, partial pressure of carbon dioxide and partial pressure of water, and you have another family of curves which these are in increasing order of L, which is the length scale that we are going to talk about next. So, this and the value of epsilon g when both CO2 and water vapor are present is going to be equal to epsilon of water that you have calculated plus epsilon of carbon dioxide that you have calculated from your previous one minus delta epsilon. So, this delta epsilon value can be read from these curves, from these graphs, and together they would give you some idea of what is the emission from a gas mixture consisting of water vapor as well as carbon dioxide or any other participating medium. So, the last thing what is remaining in our discussion is how do we get an idea of what is going to be the L, the length scale. So, what is the length scale to be used, because you are not going to get assuming a hemispherical mass of participating gas radiating and your surface of interest is at the center. That is something which is very inconvenient to use and may not be the right one, right calculation method. So, we need to get an idea of an equivalent length that can safely be used with whatever we have discussed so far. So, this characteristic length L, this is what I am going to describe to you next. So, the next one is about the next point is about length. So, what is going to be the length scale for to be used in this case? Okay. So, the concept that I am going to introduce is called the mean beam length. What is mean beam length? Mean beam length is, let us call it MBL. So, MBL, mean beam length, is the emissivity, the radius of a hemispherical gas mass whose emissivity is equivalent to the gas mass geometry of interest. So, this MBL is denoted by LE. So, LE is the radius of a hemispherical gas mass whose emissivity is equivalent to the gas mass geometry of interest. So, there is a table which tells you about the geometry, what is the characteristic length and how the beam length, mean beam length is related to the characteristic length. So, these are straightforward. The first one, let us say it is a sphere. Okay. So, the characteristic length is obviously d, which is the diameter, and the mean beam length can be calculated as 0.65 d. Okay. If it is infinite circular cylinder, and you have radiation to curved surfaces, again this is going to be d and this is going to be 0.95 d. Infinite parallel planes, so it is going to be, the characteristic length is going to be spacing between the two plates, let us call it as L, and the mean beam length is going to be 1.8 L. If it is a cube and you are considering radiation to any of the surfaces, then obviously the characteristic length is going to be L and this is going to be 0.66 L. The important one, these are standard geometries. A sphere, an infinite circular cylinder, when you are calculating, when you are trying to find out what is the radiation to the curved faces, an infinite parallel planes separated by a distance L, or if it is a cube of side L, then there analytically you can find out what is going to be the value of the LE. But if you have an arbitrary shape, of volume V and surface area A. So, it is a volume V, surface area A, then the characteristic length, as we have done before, is volume by area, that is your characteristic length, or V by A, and the beam length is going to be 3.6 V by A, and this is just an approx value. So, the mean beam length as is shown here gives you, if you look at the table once again, the concept of mean beam length is the radius of a hemispherical gas mass whose emissivity is equivalent to the gas mass of geometry that we have with us. So, the gas mass of any geometry that is available to us, if we can find out what is the corresponding beam length, mean beam length LE, then that LE would be used in all the relations and correlations that we have developed so far for the case of gaseous emission. So, the point therefore is how to find out LE for any arbitrary geometry. What we have seen is that for specific geometries like a cube, a cylinder, parallel plates and spheres, what is going to be the relation between characteristic length and mean beam length. And ultimately what we have seen is that for the case of any arbitrary shape, the characteristic length is simply going to be V by A, and what is the relation between the beam length and V by A for any arbitrary shape. The aim is to obtain LE, because if we can get LE for the enclosure surface, the volume of the participating medium inside an enclosure, then the corresponding LE can be obtained. The moment I have LE, then using the methods that I have described at the beginning, you can find out what is the value of epsilon, what is the value of emissivity of the participating medium as a function of temperature and as a function of partial pressure and so on, and what is the value of the absorptivity, what is the value of transmittivity, and everything else then can be calculated, and you will be in a position to find out what is the net amount of radiative heat transfer in between a hot gas and an adjoining surface, which is something very important that we would like to know for many of the practical gases that we come across. So, that is the end of the chapter radiation, which I wanted to tell you, wanted to introduce you to in this course. And radiation is therefore one of the very interesting, very practical branch of heat transfer that we must be aware of, that we know how to calculate the radiative heat exchange, especially for equipments involving elevated temperatures. What is the radiative heat loss or a gain? And many of the natural phenomena that we see around us is also due to radiation, how much of heat we receive from the sun and so on. So, radiation plays a critical role in engineering, in everyday life, and through the discussion of the past few classes, I think you would be in a position now to make a calculation of the heat exchange between objects, between a solid object, between solid objects forming an enclosure, and between a solid object and an adjoining gas, if the adjoining gas is a participating medium. So, that brings us to the end of this course. I hope you have enjoyed it. If there are any questions, I would encourage you to post them at the forum, and I and the TAs would try to answer them. And hopefully, this course has given you a foundation for calculating heat transfer in a variety of ways, both conduction, convection, radiation, steady state, unsteady state, internal flow, external flow, fully developed flow, the heat exchanger calculations, radiation and so on. So, best of luck. Thank you.